Hello everyone, my name is Ashfaq Ahmed and I work in the field of structural biology and bioinformatics. Today is technically part 11 of the computer-aided drug designing. But in today's tutorial, we will learn how to perform ligand-based screening with neural networks. What actually are neural networks? It is a subdomain of artificial intelligence. This is the shortest possible definition if you don't know. Okay. Let me tell you in the start of this video that today's tutorial will be potentially a bit longer because I will try to give you some basic introduction of the different aspects of the neural networks and model building, model compilation and optimization if you don't know, and if you are already aware of that, so possibly the starting point could be a bit boring for you, or you can forward this video. So let's start. So first of all, we have to head on our Colab repository, that is H100 GitHub repository, that is H100. Okay, possibly I'm not signed in, so okay. Now from here I will drop this link in the description section of this video, so you can just copy paste in your browser and it will work. Okay, now you have to click here the cat project, then you have to scroll it down and check part 11, ligand-based screening using neural networks, part 11. Part 10 was technically this one, the binding site detection with AlphaFold 2. Why I stressed there again? Because the thumbnail was different, so if you are not aware, you can watch it. Okay, oh sorry, I click part 8. Okay, part 11. Now you have to click connect. Okay, but we have some theory in the start, so therefore I will not connect it now. Okay, what is the aim of this tutorial? And this is just a basic introduction, you can read. What is the aim of this tutorial? The aim of this tutorial is to use deep learning. It is actually not a machine learning, but you can call it a machine learning as well, but neural network is a type of deep learning. So nowadays machine learning and deep learning, both of our other similar models or other similar processes are getting famous in every field of science and also in pharmaceutical research. So we will use the same EGFR receptor, and we will try to learn that how we can use neural networks in our research. Okay, this is the background, but we will study it here, and so let it be. Okay, these are the references if you want to read. Okay, what package we will use? We will use RDKit and Keras library sequential model from the Keras and some model training and APIs. Okay, what is the let's start. So from the biological background, EGFR is the epidermal growth factor, but I will not talk about it because this is part 11, and from the part 1 we are dealing with the same protein, so we talk so much already, so that's it. Okay, compound activities Meyers, I have already talked about these two, IC50 and PIC50, in a very good detail in part 1. So if you are watching this tutorial for the first time, I would strongly recommend to first watch and to perform the part 1 tutorial. You can click it here and it will lead you to the YouTube video directly. Why? I'm not asking you just for the sake of views or watch time, but the data we will use here, or the starting data we will use here, is actually downloaded in part 1, or we have downloaded already in part 1. So we will start from there. I also tried to merge those steps in this notebook, but then I felt the notebook became a bit longer, in fact much more longer. So that's why I thought not to do it that way. Ask you guys, if you are new here, just you are requested to run the part 1 first, or to watch that video, because if you don't have the data, then you may not be able to run or to understand this notebook. Okay, but how to generate data you will learn in part 1. Okay, so then we will use some molecular encodings. So what are molecular encodings? I have already talked about in part 3. If you remember, if you are watching this series, then in part 3 we had talked about some max and some smarts, and we call it fingerprints, and so here we call it molecular encodings, or you can call it the fingerprints. So we will also calculate those fingerprints in this tutorial. So I am also not going to go sufficient detail here, because they are all already available in part 3. Now I will give a much more detail about this topic, because this is a new topic in this series. What is a neural network? A neural network, it's actually designed, or the idea is taken from the human brain, or from the human brain network. So therefore they call it a neural network, but they are also called artificial neural networks, or ANNs. Okay, they are the subsets of machine learning algorithms, or the deep learning algorithms. But what is the difference between the machine learning algorithms and the neural networks? The machine learning algorithms simply one use a model and ask the model or train the model and then test the model. That's it. This is the simplest definition I can give. But what is the difference in neural networks? The neural networks basically works in layers. If you can see this figure, this is input layer, this is hidden layer, and this is the output layer. So let's first talk about the input layers. The input layers takes the features. Now what are the features? In the scenario of this particular tutorial, if you remember the part 1, so we had a data that contains the Kimball IDs, that also contains the smileys. The data will be here, so let me open it. So we had this kind of data. Wait. Okay, so we had the molecular Kimball ID, and we had some smileys, and we had some PIC50, also IC50, etc., etc. Okay, so if you input this column, then it means the molecular Kimball ID is a feature. or if you input this column, the smileys, so it means the smileys are the feature. So features are actually some specific characteristics in the data that you will input that to the neural networks or to the input layer, and every feature will be taken up by a single, you can call it node, but in terms of neural networks we call it neurons. So every neuron takes up the input. And what is the input? The input is some specific feature from the data, and every feature should or will have some weightage in the form of some number, weightage in the form of some information, and we call it weight. So every input will have some weight W. Okay, now then comes the hidden layer. So why neural networks are a bit advanced in my view than machine learning? Because it uses the hidden layers. What are the hidden layers? It is up to you that how much or how many hidden layers you kept. In this figure you can see H1, H2, H3. So 3 layers of neurons are present in this figure, or 3 layers of hidden neurons, or 3 layers of three hidden layers are present in this figure. It can be increased to 5, 6, 7, 8, and so on. So basically, if you ask me that up to how much we can increase it, so it's belong to the data, and there is no rocket science that you will decide in advance that 3 layers, 4 layers, 5 layers, 6 layers, because it's just a hit and trial method, or we call it optimization. So we will learn it in today's lecture or today's tutorial. So the hidden layer, basically we started from the minimal value 2, 3, 4 based on our data. If we are inputting, or if we input many features in the data, let's say like this, if you provide 2, 3, 4, 5, 6 features or even more in your data, from your data, and you want to predict something, some output, then of course you has to tweak these hidden layers, and you have to change these hidden layer or the architecture of these hidden layer. Okay, what will happen if you increase the hidden layers? So obviously your computation time will increases with the hidden layers. Now your features on input features will be subjected to the hidden layers, and then the hidden layers will generate some uniform output. So once again, it is up to you how many output you need. So you will also ask the neural networks. Okay, so let's understand piece by piece. It was a general introduction I could give that what actually are neural networks or artificial neural networks. So we will use some input neurons or input layer. So this is the input neurons or input layer, and these layers will always take the features, and you will decide what will be your feature from your data, and on those features you will make some prediction, and every neuron will take one feature. Then we will have some hidden layers as I discussed above. So all these things we have discussed, that it's up to the data, it's up to the experiment, and it's a trial and error method, and you have to tweak these hidden layer if you are not getting good results. Okay, and then finally we will have some output neuron or output layer. So in the output neuron, In this particularly in this experiment, we will try to predict the PIC 50 value, and what will be our feature we will look in this tutorial we will learn. Okay, in the once again there are many output functions, numbers of output functions, but we will discuss, or I will just give you a brief introduction of this one. For example, if your output feature is a vector value, or a real number, I would say, for your understanding, then we call it a kind of regression task. Okay, but sometime some people use neural networks for the binary classification. Binary classification means, for example, you have some data. Okay, let's explain binary classification in terms of this data. For example, if I categorize all the PIC 50 values in my data downloaded from the Kimball, and if I categorize in intermediates, in active and in inactive, let's say I make some boundaries like above 5 is active, and in between 3 to 5 is intermediates, and below 3 is inactive. Then if I ask the neural networks just to classify what compounds will be active, what compounds will be inactive based on some features, then this will be called a kind of binary classification task. So, and then sometime in our data we are dealing multi-class classification. Multi-class classification, simply if I explain it this way, it will be a kind of, if your data, if you also want to classify based on, let's say, gender. So if you have some data, you also want to classify based on gender, based on color, based on height, based on weight, based on some behavior, some sleeping, some wakening time, and so on. So this is a kind of multi-class classification. So of course you will have maybe many features, and then you will use many hidden layers, and of course it will increase the computation time. Okay. Okay, let's I will give you some much little more introduction. So for example, these x are our features, x1, x2, x3, or xn up to xn, and they have some weight. So the weight of this feature will be w1, w2, and wn. So when this feature, when we uploaded this feature, then the neural network will add some value, and we call that value a bias value. What will happen? This is the hidden layer. Okay, now here we provide some feature with some weights. Now when it reach here, so the computer will add some another value to each feature. We call it a bias value. Okay, so then now they are in the hidden layer. So h is equal to, that will be weight 1 of feature 1 plus weight 2 of feature 2 plus weight 3 of feature 3, and so on, plus b. B is actually that biasness value, and this is some summation of all the 3 feature along with their weights plus the biasness value. Okay, now the point is that the weight and biasness in a neural network are referred to as learnable parameters. Okay, what I mean from learnable parameters, because the neural networks or the AI or machine learning, they are not a rocket science that you will develop a model and you will run it and that's it. No, you will be extremely lucky that if you developed a model and it worked um, the best. And but what you will do, because you will develop a model, you will test. If you are getting good training and test result, then you will save that model and will test that with some unknown data or with some unknown compound in our case, and you can also use that model in your future studies. But it takes time to optimize the model. So because this biasness value or this bias value that sometime disturb on a larger scale, and you are not getting a balance uh, between a good model to treat your data. But how we will learn that what is a good model, so we will discuss it in the next section. And so therefore we call it learnable parameters, because we will learn with time that if I increase this, so what is decrease, if I decrease this, so what are increase, and we call it model tuning for good performance. Okay, what is an activation function? When we upload our features from the input layer to the hidden layer, so we use some activation functions. There are many activation functions, but in the simplest definition will be like this: input, it's the hidden layer or neuron, and we also use some activation functions. The activation function is a kind of sigmoidal. You can see these curves, and then they will produce some output. But there are many activation functions, but the most people use it, we call it ReLU or rectified linear unit. And this is the formula. If what activation function do, if for example, it is the simplest understand for your simplest understanding, if x is positive, what is x? X is a kind of feature we discuss in the start. So if the feature is positive or maybe 0, so the ReLU will give kind of that positive or 0 or up to the infinity. So you can also read, because I'm trying to be quick. So these are, we will use ReLU functions or ReLU activation function. I also suggest that only do not use this tutorial if you really want to work. So you need to study some literature, some paper, so it will also increase your understanding. So I would suggest use this tutorial as a landing pad or as a stepping stone in this field. Okay, now this is a linear activation function. So this is, it has a into x is equal to x, and most of the time we use this function in a linear regression. Okay, now one final thing, what is loss function? Now I told you that in the start I told you that the network will also add some value. We will call it a kind of bias value. So as per that value, sometime or not sometime, actually most of the time, the predictions are not perfect during training. But how we will know? We will know from these two values. One is mean square error or MSE, and another one is mean absolute error. So mean square error means that when we are in the stage of training the model building is very easy. But when we are training the model, so in, at that time, what we do, if we have, let's say, 100 features, let's say, or if we have 100 rows in our data, 100 compound, let's say, then we will say like 70 compounds for training and 30 compounds for test. So when we ask the computer that randomly use 30 compounds for the test and 70 for the training, so what the computer will do, the computer will, or the model, I'm sorry, not the computer. So what the model will do, the model will first train on those 70 compounds, and then the model will predict the values or some outputs for those 30. But remember, we already know the output values of those 30. So then we are actually testing the model, that how it will behave. It's like this. For example, if you are in an interview, and if the interviewer asks you that who won the football World Cup in 2022, I guess, yes, in who won the football World Cup in 2022, so actually he knows the answer, but he asked you to test you, that how you will answer, or how much is your correctness, I would say. So it's just like the same thing. So first we take the data, we make a model, we train the model on some data, and we keep the other part of the data, let's say 30% or 20%, and we ask the model to predict for this data. Then we compare that how much the model performed. Is it better or not? So we will know about the difference in the real values and the values generated by the model in the mean square error. And those mean square error are then calculated for the absolute error, or absolute error are actually the mean of MSE. And from there we decide that how the model is behaving. If the error is on the higher side or more than 1, what we do, we just go back to our previous step and we tweak some things. We change the activation function, or we increase some layers, or we did we increase some input neuron, etc., etc. And this is a hit and trial method, as I told you in the start. So once your error is minimized to below 1, I would say, or the lesser the better, then you can save that model and you can use it for predicting the unknown compounds or the unknown stuffs you have in your data. Why I use compounds? Because we are dealing compounds. Okay, now this is the step that we will train the neural network, and then we will test some data, and we will check the loss of function in terms of MSE and in terms of MAE, and we will go for the one which is the minimum error will be the better one. This will be your computation task. So normally the computational task is on a higher side for the neural networks as compared to the machine learning. So what we do, we normally study the model on the batch. Just randomly we ask the program to check this batch, to check this batch. Batch means, just like I say, if I have 10,000 compound, so I would ask just take it 64 from the training and testing data and tell me what is the real situation, just like this. Okay, what is Keras? Keras is actually an open source library for machine learning and for neural networks. And it's, if you don't know library, or if you are a biology student, so simply it's just like the collection of all those files which works for four things. What four things? Prepare the data, define the model, then run the model. We call it compile the model, but simply you can say run the model. Then fit the model. Fit the model means just evaluate the model on some training data and some test data. Okay, normally people use 70 to 30 ratio or 80 to 20 ratio. 70 for testing and 70 for training and 30 for testing, or 80 for training and 20 for testing. Okay, and then finally we evaluate the model. But what we will evaluate, I told you these two things, MSE and MAE. And if the model is performing better, then we will do our predictions on the unseen data or the unknown data or the unlabeled data, what you call it. Okay, so I have connected this thing and the notebook. Now we are going, these are some application, blah blah blah. So now we are going to install some program. It will be quick, but still I will pause during the installation to save your time. Okay, welcome back. Our installation is completed. It took almost 2 minutes. Okay, I normally clear this log. Okay, so up to this import step. Now we are here to the data preparation. Our data should have three columns: Kimball ID, smileys, and PIC50, as I told you here. Now what will you do? Here we will use the data produced in part 1. So if you have the data, then you will need some minimal editing. If you don't have the data, then you have to go back and run part 1. Okay, once you run successfully the part 1, then download the CSV file into your computer, which is mentioned in that video. Then open the CSV file, and from there on you will also see IC50 column in the data and some nanometer or NM column in the data. So just delete these two columns, then you will left the 3 columns: Kimball ID, smileys, and PIC50. Save this file, and then we will upload this file here. So I have this file already here, so I will upload it to the sample data. And the file, this is EGFR compound underscore new. Okay, because I have tweaked these things, so in your case you have to change this name, or even if it gives some error, then the simplest way is to, if this is your file, then click here, copy path, and from here to here paste it. Then click here click here. So it will gives you that you have 7074 rows, and it means 7074 compounds or bioactivity data and 3 columns. Okay, you can just look the data. So just some of the lines: Kimball ID, Smileys, PIC50. Now keep the necessary column. I asked the program that keep the Smileys and the PIC50 column here. If your data has this column name, let's say canonical Smileys, then it will generates an error. So in that case you have to edit the Smileys into canonical Smileys. Okay, now we will perform some molecular encodings. What are molecular encodings? I have discussed in the start that we will generate some fingerprints for these 7000 plus compounds which is present in our data. It's done. Now here we have just create an API token, and now here we are performing calculating the fingerprints using all those Smileys. So now you can see an extra column, fingerprints underscore df or data frame. So you can see some extra column is generated here. So it's generated for all the 7074 compounds, and these are the fingerprints. If you don't know about the Max or the smarts fingerprints, then I would suggest to go and watch that tutorial number 3, part 3. Okay, now we define X. I have already discussed what is X. X is the feature. So we will define now the feature, and Y the target data, which will be used to train the model. In our case, we will use 70% of the data for training and 30% of the data for testing. So it means in the 7074 compounds, the model will be trained on 70%. The computer or the model will calculate the 70% for itself. Okay, now here we ask the program that the feature will be the fingerprint, which is associated with every Smileys we have generated here. Where? Oh, I think I have cleared it. It's okay. So the feature will be the fingerprints associated with all the compounds we calculated above, and the output will be PIC50. If you want to change the test size, let's say if you want to make 80/20, then make this 0.3 to 0.2. If you want the test to be minimum and the training to be more, like let's say 90%, then make this 0.1. 0.1 means 10%. Okay, now we ask the program, okay, the computer split the data into two. The training data will be on 4951 and the test data will be 2123. Again, you can change it here. Now here, as I told you, we will perform 4 steps. The data is prepared now. Now we will define our model. In fact, we will kind of generate our model, and then we will compile the model. Compile means we will run the model. We will fit the model. Fit the model means just training and testing the data, and then we will evaluate the model for those MAE and MSE. Okay. Now, in defining the neural network model, so once again we will use some hidden layers, and we will use two hidden layers. In the figure I showed you, it has three hidden layers, but that was just a figure. So model will be of sequential type. If you don't know sequential type, just I suggested you already that you will need to read some literature, because if I start explaining each and everything, then it will take not 1 hour, it will take many hours. Even I have those resources. If you are interested in learning this thing, then while accessing this GitHub, don't enter to the CAD, just enter to the BioPython, the first one, and there you will see too many neural networking stuff. Just open it and work on. You can learn on it. You can learn the neural networking there. There are sufficient details, or even more sufficient detail, but why I'm not still covering those videos, because most of my users are from biology background, so I don't want them like they feel like I'm kind of alien to them. So that's why I'm trying to stay relevant in our videos with biology. Okay. So the model type is sequential. Then the first hidden layer, the activation function will be ReLU, hidden layer first, its name will be layer 1. As I told you, we use two hidden layers, so the second hidden layer will be also activation will be ReLU, and it will be layer 2. And then the output layer will be, the activation will be linear, and we will call it 3. And then finally, we ask the computer, the script, that compile the model, and you will also need to calculate the MSE and use some Adam optimizer, and I will need to know the MSE and MAE. So just run this. So we just created a model. Now we will use training our model, and we will try to use some mini batches size, and then we will train the model on the whole data. But then for the plotting purposes, as I told you, that it will take longer time, so that's why we will use some batch sizes. Let's say I'm using 3 batches, 16, 32 and 64. If you want more batches, you can include, but it's better to keep this in a multiple, like 16 2s are 32, 32s are 64, and then it should be 128 the next batch if you want. So you can, and this is the number of epochs, that will be 50. I did not explain it, it's not necessary right now. And we will have the layer 1 size 64 and layer 2 size 32. What are these? These are actually neurons in layer 1 and layer 2. Okay, the hidden layers, in fact. Okay, now calculate and plot. So you will see it will take some time. So if I increase these batches, it will take much more time, so that's why I kept here. It will still takes time, 2 to 3 minutes. So let me pause this video. Okay, welcome back. It is completed. It took almost 2 minutes, and it has generated these 3 plots. So if you see these 3 plots, this is the batch 16, this is the batch 32, and this is the batch size 64. The blue one is for train, the red one is for test. what was the test loss? This was 1.06, 1.02 and 1.03. Test loss is actually that error. Okay, so now if you see, the lowest test was this one, test loss 1.03. Now from here on, if you want to optimize this model more, you can do it. Once again, if you want to generate more batches to see how it will behave, just increase another batch 128 and then increase another batch just to see if the model behaves better or not in some batch, but I don't think so. But so you have to tweak, or you have to learn how to optimize the model, although it is not very bad model, because MSE1 is somehow acceptable, but it is also kind of borderline. It's better to be lower than 1. Okay, you can read this. So we have this batch has the lowest test loss, or the MSE. So therefore what we do now, let's say our model is optimized here. This is the test loss with 64. We prefer this one. Then what we do here, we will save this trend model. For example, we like it. Now we will save the weights of this trend model. So here I will save it. Its name will be weights.h5. This is just kind of extension, weights.h5, and its name will be best_weights. And we ask to use the batch size 64. So remember, if you are tweaking the batches, or if in your case the best answer is, let's say, in batch 16, then you have to change this 64 to 16, because if you just run this, then it means you save the weights from the wrong batch. Okay, so I have 64 because the test loss is minimum in batch 64. It will take some time, because it's actually saving weights of the model. Also, we fit the model here on this batch 64. Okay, now refresh here to see something new. Okay, this is the model weights, best weights, with the kind of extension weights.h5. Okay, now we will evaluate and predict on a test set. This is interesting. Okay, now let's say we generated a model, we prepared the data, we generated a model, we fit the model on a specified batch. In our case that was 64. I don't know what will be in your case on your data. So now I want to use that model. So how we can evaluate the model? So first we just ask the program to be ready yourself, and you have to answer me in the form of MSE and MAE. And now I'm going to evaluate the model on the test data, so you have to print this thing. So just we ask it to okay. Now okay, I'm sorry, this was not the test evaluation, this was just the evaluation of these runs. So if you can see, this was the overall loss, the MSE was 1.1, and the overall absolute error was 0.8. I think it's below than 1, so it's acceptable. You can see the mean absolute error or the MAE on the test set is below 1, which give the range that PIC value is pretty much lower, because this error actually means, I explained in the start, that for example the real value of PIC is 6, and it will generate maybe 5.2 or 3 or maybe 6.7 or 8, just like with this difference. So it's not a big difference. That's the real reason, or that's the reason what actually the MAE means, or why we care about the MAE. Okay, now we are going to predict the PIC value on a X data set. Okay, so we will run some predictions on the X data set. So first we will run this. Okay, it's not the X data. What actually is the X data set? Just give me a minute. Sorry for confusion. Actually it's a bit late here, and I did not make a video in the last week or so, so you guys were messaging me, so that's why I'm skipping my tone my words, I would say. Okay, what actually is the X test data? The X test data is actually this data, the 30%. So it says like on the among the 30% data, these are your predicted PIC 50. Why only these 5 or 6? Because we asked to just print first 5, or you can increase, but that doesn't matter. These are kind of useless stuff, because we already know the loss and MAE. So even if you do not run this, that's okay. Okay, this is an important step. This steps will tells you that how your model perform, because I told you that all of the data contains PIC 50 values. We all the 7074 compounds, but we ask the programs, don't read the PIC 50 value of the 30% compound, read and train and remember the PIC 50 value of those 70% in the training data, and link this PIC 50 value with the fingerprints. Now in the next step we ask the program, okay, just read the fingerprints of those 30% and predict the PIC 50 value. And then finally the program compare its own result with the real result, and they gave us the MAE. Now we plot those results here. So if you see this straight line, how to understand, this is the true values and this is the predicted value. For example, I would say like this, you can see this dot. So the true value is, you can see it is just like if I say maybe 3.2, I would say 3.3 or 3.5, whatever you say, this one. But the predicted value is 4.5, so almost one error. So this is how to read this figure. I just explain it. So the dots, the more the dots are near to this line, it means the better the model is. I think this is better, because except few dots like this one, because this dot is away from this line. So if you read it, the predicted value is almost 0.5, I would say, but the real value is 4. In fact 5.8 something, but they are very few. You can see they are very few. So this is how you can interpret this figure, that the true values, predicted values in our 70-30 ratio. You can also train the program by going back to the previous training and testing step and tweak the values. Let's say 80% training and 20% testing. Let's see you are getting better results or worse or same results. Okay, and for the third time I asking you, just also read something and just to learn something how to tweak the model. Okay, now there is a positive correlation for most of the dots, so it's, I think it's acceptable. Now here we are going to save the model, and then we will save these weights with this model. So click here, save model to test. So we should have some new entries here. Okay, model JSON and model weights 5. Okay, now until now what we learn, just hold on, we are just 5 to 6 minutes away, and then we will finish this tutorial. Until now what we have learned some basic introduction, then we prepared some data in part 1, we use that data, then we train the model, we generated a model or we make a model, then we train the model with 70-30, then we just analyze the MSE and MAE, then we plot. Now let's say we have saved our model and weights. Now we are going to test this model with some unknown data. Now I have this unknown data. I will teach you how to prepare this unknown data. This is the, you have to open the Excel file, new, then Microsoft Excel, and what you have to do, just make one column. This will be the index column 0, 2, 0, 1, 2, 3, start from 0. Then in column B you can call it, let's say Pubchem ID or whatever name, whatever you like, and this column will be the canonical smileys. And from where you will get these smileys? From the Pubchem. That is very easy. Just let's say you have the library of compound, so you, from the Pubchem you can search its name. But I also teach you, I have also covered another tutorial just long ago, 3 to 4 months ago. The tutorial, if I tell you this one, I'm not good in editing, so I will show you this way. It will works for you, that's why I'm showing you how to mine Pubchem database for similar compounds. For example, you have 10 compounds. Why not use this notebook? Why not use this tutorial? And for those 20 compounds, generate 100 similar compounds or extract 100 or 50 similar compounds. So now in this case you will have, if you have 20 compounds, you extracted 50 for each, so 20 multiply 50, that means you have now the library of 1000 compounds. But also this module or this notebook will give you this file directly of 1000 compounds, so you will not need to generate it manually. Once you have this compound, if you generate it manually, then it will be in XLX format or the Excel format. Click save as, then the directory you want to download, then here you select the CSV comma delimited and then save as. Once your file is ready, now this file is ready with me. Okay, I will upload this file here. Let's say upload the test file. I have just made these 4 to 5 for you. Okay, so these are the new compounds. They are not present in, maybe the gefitinib is present, but the ibuprofen, pyrazole, and I don't know the chlorophenol something, but I just name it chloroP. Okay, then this is the test. Click here, copy path, and then paste it here, run it. I did not paste because I have already this. Okay, now you will see all your data here. Now convert your smileys into those fingerprints. Now load the same model we just created. So now we loaded the model from the disk, and do not use this, it will generate error. So I'm deleting it here. I will fix it, but it will take some time. But right now you should know, do not run it here again. Okay, now we will do some prediction on these unknown compounds. Okay, the prediction is done. You can see a new column. It says gefitinib will give you 6.9. That's interesting because this is the EGFR inhibitor, and then the brufen is the lowest, and the pyrazole something is 6, and this is 6.2. Now we ask like to save the predicted values. If you want to test this predicted values, then you can save it. Let's say click here, and you will have this data here. Wait, click refresh. Okay, predicted PIC 50 value. Now if you want to see the compound, so I will just read the top 3 drugs here. If you want to read more drug, let's say this is 3, so you can tweak this number. So these are the top 3 from the list, which was initially 4. Now draw the compounds of these top 3. So this, it will be drawn with the predicted PIC 50 value 6.2, 6.94 and 6.09. Okay, you will also see, or you will also observe some similarity in structure in your real data, because why not we are seeing some similarity here, because I just randomly select these 2-3 compounds. So now if you are following my tutorials, so the funny thing I need to share with you, I taught you how to predict proteins, I taught you how to do some CAD things and how to automate the docking stuffs. But what is the most important thing left? Do you know? Just for a fun. It also means that now constructing a library of unknown compound is a real task now. It's not actually for a fun, because in my research to my students, I stress the most on this part. Normally people I know, they just pick compounds from zinc or somewhere else. So this is not the real way. The real thing is to generate a good library first. Okay, so I hope you are not bored with me. If you like my way of teaching or instructing, whatever you say, then please subscribe this channel and share this channel, and thank you so much for watching this 1 hour video. Okay, bye bye. If you have any question, please ask. Bye.